Welcome to the topic on finite element method for structural dynamic analysis. My name is Muttanna Bandal, SG Balekondra Institute of Technology, Belgavi. To understand the dynamic loads, let us define what is a dynamic load. Dynamic loads can be referred as the loads that may vary with the time and they have a magnitude, direction and or a point of application of a load that changes with the time. Under the action of dynamic loads, the structure vibrates. That is, the structure develops a significant level of inertia forces and significant level of mechanical energy stored as a kinetic energy. So, to give an example, if you have traveled in a bus or in a bike, you may experience dynamic loads when they are when the vehicle moves over humps. So there the loads will be varying and you may feel the inertia. Suppose if the bus moves over a hump, there is a sudden jump and the mass of your body will gain a certain inertia force, and when you come back on the seat you may feel the pain of the inertia force. So this you may sense what the inertia force is mean by. Similarly, when the body is moving with a certain inertia, it gains the kinetic energy. So basically the dynamic loads give rise to the two significant forces. One is inertia force and another one is kinetic force that is applied on the body. So to give an example of a dynamic load, earthquake loads on the building, bridges, dams or plants, power plants are the examples. Like when the earthquake happens, the building starts shaking or bridges will vibrate, and similarly the dams may experience the earthquake loads. So such kind of loads are referred as the dynamic loads, or wind loads on a long span of a bridge or a tall chimney. So this can be seen like in a north part of Karnataka. If you have visited the Gokak Falls, wherein there is a hanging bridge, and the hanging bridge will experience the dynamic load whenever the wind loads will whenever the wind loads change their magnitude. So such kind of loads are also referred as dynamic loads, and loads due to the blast and impact and running machineries in a building. Suppose if you enter into a machine shop, you may experience the some kind of vibrations that comes from the machines. Like if you are standing on the bed, the near to the bed of the lathe machine, you can experience some kind of vibrations that comes from the machine. So such type of loads are also called as a dynamic loads. And also the whenever you are moving over on a vehicle and that are moving on a bridge, you can experience the vibration, or the bridge may also experience the vibration. So these are some of the examples of the dynamic load. So to understand the behavior of the structure under the dynamic loads, we have to define some terms called as degrees of freedom. So degrees of freedom can be referred as number of independent coordinates required to specify the displacement at all points in system and at all times. So here you make a note of this all times. Let us consider an example. So here there is a mass m and it is attached to some kind of a spring, and other end of the spring is constrained, means which is constrained in all direction. So under the external force F of t, so F of t refers to the force that is varying with the time. So under the action of external load, this mass will move back and forth, whose displacement is given by u of t. So in the sense, the number of independent variable, that is degrees of freedom, here in case is a u of t, which will explain the back and forth movement of the mass. So we say this is this for this system 1 degree of a freedom exists, because u of t will give a displacement of the mass in a horizontal direction, which is back and forth. And also we have told about a with respect to a time also, in the sense this displacement is not constant, it will vary with the time, and that defines the dynamics of a system. So in the sense, degrees of freedom will help to understand the displacement factor as well as the velocity of the mass. So when we define a velocity, the dynamics comes into a picture. So it becomes very important to understand the degrees of freedom of a system and then move further. To represent the structure in a mathematical model, let us consider like whenever a structure vibrates, it not only displaces but also accelerates. Like in a previous case, I told like the it not only gives the displacement but also gives the velocity, and when the velocity varies with the time, it gives a acceleration also. So whenever a structure vibrates, it not only displaces but also accelerates. Besides, the mechanical energy is converted into a heat or a sound. Suppose if I consider a tuning fork and hit the tuning fork with a pad, you can see the vibration of the tongs of a tuning fork, so which vibrates in a transverse direction, and that transverse direction, that vibration of the tuning forks will displace the air particles in the atmosphere, and that gives rise to the sound. So in the sense, whenever the structure vibrates, either it produces sound or some of the mechanical energy is converted into heat. So to understand the behavior of such a structure, here we define some of the properties called as a stiffness, inertia, and damping. Stiffness always resists the displacement. In a previous case, here the stiffness of the spring, it will try to resist the u of t. So hence stiffness resists the displacement, inertia resists the acceleration. Like this motion, the mass will resist the moment, or it resists the displacement here in this case. So that gives rise to the inertia part. And damping here can be the friction. Here the damper is not shown, but there will be some kind of a friction between the roller and the support. In the sense, some of the energy is dissipated in the form of friction or a heat. So that part we call it as a damping. In the sense, it dissipates the energy. So inputs to all these things to happen is a external force, so which is f of t. So f of t acts as a external force, or we call them as a initial condition. So also the mass offers resistance to acceleration and it stores a kinetic energy. Suppose if I take two spheres of a different mass, one of say 100 kg and another of 10 kg, if I allow the two spheres to roll through a slant height, obviously the mass which has a more mass will gain a more acceleration, and it tries to store the kinetic energy over a period of time. and this can be felt. Suppose if I try to stop both the spheres, the sphere which has a large mass will impact more, or will impact a more force on your palm or on a stopper. Similarly, a damper dissipates mechanical energy, spring offers a resistance to displacement and stores the potential energy. You see here, the mass stores the kinetic energy and spring stores the potential energy, and force or the initial displacement or a velocity supplies the mechanical power. So this is basically a external force. So we should understand these four terms. So mass, damper, spring and the force. All these four terms can be modeled to represent a vibrating system in a mathematical form. So the dynamic structure, the dynamic behavior of any structure can be explained by the Hamilton's principle, which will help us to derive the equation of a motion of a dynamic structures. So it can be stated as, for an arbitrary time interval t1 and t2, the state of motion of a body extremizes the functional and is given by I is equal to integral over a period of time t1 to t2 into L into dt, where L is called as a Lagrangian and it is given by L is equal to T minus phi. T refers to a kinetic energy, phi refers to a potential energy. So to understand this, let us consider, like, if I take this as a time factor t, so I will say this as a t1 time t1, this is a time t2, and here is a displacement u of t. So y-axis is a displacement, x-axis is a time interval, and there are two time t1 and t2. So integral of t1 and t2, and here let us consider there is a mass m. When I apply a load on this one, or when this mass is disturbed by external force, it moves with a certain displacement or velocity or acceleration, and it goes to a new position, say at a time t2. Now the displacement or the movement of the mass from t1 to a t2 can be in a can be moved in a different paths, like it may travel in this path in this way, it may travel in this way, or it may travel in this way, or it may travel in this way, or it may travel in a straight path. Now we don't know how the mass moves from this position to this position over a period of time. These might be the possible paths, all five, 1 2 3 4 5. Now the Hamilton principles help us to help us to exactly define which path the mass has taken place. So obviously, whichever is a minimum path, that path will be taken by this mass from to move from this position to a T2 position. So that is the explanation of this statement. So in the sense, for an arbitrary time interval from T1 to T2, from this time to this time, the state of motion of the body, which path it takes, can be found by this functional, that is I, where integral of t1 to t2, L is a Lagrangian, which is basically gives the energy factors, which is kinetic energy and as well as the potential energy. So Lagrangian L is defined as T, kinetic energy minus potential energy. Now, if L can be expressed in terms of generalized variables Q1, Q2, Qn, Q1 dot, Q2 dot up to Qn dot. So here Q1 and Q2 refers to the displacement of a mass 1, Q2 refers to the displacement of mass 2. Suppose if I have a two masses like this. This is M1 and this is M2. So Q1 might be the displacement of mass 1, Q2 might be the displacement of mass 2. Similarly, Q1 dot gives the velocity of this mass 1, Q2 dot gives the velocity of the mass M2, where Qi is equal to dq by dtt, dt. Then the equation of motion are given by this term, d by dt into dou L by dou Q dot I. So this is a velocity term minus dou L by dou Qi. This is a displacement. So this refers to the kinetic part and this refers to the potential energy part. So with this, let us illustrate the Hamilton's principle for a two-point mass spring system. Let us consider a spring mass system with the two masses m1 and m2. Let m1 displace with the x1 factors and x1 dot refers to the velocity of the mass m1. Similarly, x2 is the displacement for mass 2, x2 dot is the velocity for the mass m2, and k1 and k2 are the spring or the stiffnesses of the masses. Now kinetic energy T for the given system can be written as 1 by 2 m1, so x1 dot square. So it is basically the kinetic energy is given by half mv square. So m1 is written here, x1 dot is nothing but the velocity of the mass m1, that is x1 dot, plus the kinetic energy of the m2, half m2 x2 dot the square. Similarly, the potential energy of the system can be written as phi is equal to 1 by 2 k1 into x1 square. K1 refers to the stiffness of the mass spring 1, that is k1, into x1 is the displacement of the mass m1. So it will be a k1 x1 square plus 1 by 2 into k2, so this spring, and the net displacement of this spring. So basically it is x2 minus x1. Suppose over a period of time, let the mass be this one, like it has traveled x1 and this can be a x2. The initial position was here and this is a x2. So the net displacement, that is this displacement, is x2 minus x1. So that is written here, 1 by 2 k2 into x2 minus x1 the square. So these are the energy terms, which in other sense this will define the Lagrangian. L is equal to T minus phi. Now using L is equal to T minus phi, we obtain the equation of motions as this. So from Hamilton's principle, d by dt dou L by dou x1 dot minus dou L by dou x1 is equal to, so m1 into x1 double dot. So if we remember, like when the structure vibrates, I told it not only displaces but also accelerates. So there is acceleration part. So in the sense, this equation m1, when we when the structure vibrates, the mass m1 has a certain acceleration. It gains the inertia. So that is represented by x1 double dot. X1 double dot is nothing but acceleration. So m1 into x1 double dot plus k1 into x1 is a storage potential energy of a mass 1 minus k2 into x2 minus x1. So these terms are basically taken from this. So if I want to say what is the energy stored in this one, I can say k1 into x1 minus this part, because some of the energy is stored by this one. So it is connected. So I should negate the stored energy of this one minus the stored energy that is because of a k2. So because of that, it is written as k1 x1 minus the energy stored by the spring k2 is this factor. Similarly, if I consider a mass 2 m2, m2 into x2 double dot, acceleration of a mass m2, plus what is the energy stored in the k2, that is k2 into x2 minus x1 is equal to 0. Now these two equations can be written in a matrix form as m1 into x double dot 1. So if I multiply this row and this column, I'll be getting this equation. So m1 into x double dot 1, so this term, 0 into x double dot 2 is 0. So there is no m2 term here in this equation. So hence this row satisfies this. Similarly, if I come to the second equation, there is no m1 term here. So it is, or x1 term here, 0 into x1 double dot. So it is 0, m2 into x2 double dot. So this term is appearing. So in the sense, this gives this 2 matrix will satisfy these two uh, components in the above equations. Similarly, coming to the potential energy part, if I multiply this one like k1 x1 minus k2 into x2 minus k2 into x2 minus into minus plus k2 into x1. So if I say this and this, there is x1. So therefore k1 plus k2 and x1 is a common. So I have written that here k1 plus k2 into x1. So I am satisfying these two terms. And there is another term minus k2 into x2. So minus k2 into x2, this row and this column. So will give a potential energy of this. Similarly, coming to this point, minus k2 into x1. k2 is there and minus x1. So minus k2 into x1 plus k2 into x2. This into this. So in the sense, these two equations can be represented in a matrix form as this. Now rewriting all these equations, so this is nothing but acceleration, this is nothing but the displacement components, and these are the property of the structure, that is a stiffness property of the structure, and this gives the mass property of the structure. So that can be written as M mass matrix into acceleration x double dot plus stiffness property capital K into x displacement is equal to 0. So where M is a mass matrix, K is a stiffness matrix, and x double dot and x represent acceleration and displacement respectively. So hence the Hamilton's principles help us to derive a equation of motions of each mass in a structure. Now going ahead, we will derive what is called as a consistent mass matrix. So consistent mass matrix refers to, like suppose if I take a cantilever beam like this, it has both the property, K property, stiffness is also there, as well as it has a mass, but the masses are distributed over a length. So we cannot say this as a one mass and this as another mass. So in the sense, such kind of structures wherein the mass is distributed over a structure, we call that as a distributed mass structure. For that we have to define what is called as a consistent mass matrix. So to do that, let us consider a solid body with the volume dV. Small dV we will take, like if I take this cantilever beam, we will consider a small length dx, and this is how it looks like in 3D, and this is a small area for cross section. So A into dx will give a small dV, that is a delta volume. The kinetic energy is given by T is equal to half mv square. So here u dot t refers to a u dot transpose and into u dot. So u into u will give a u dot into u dot will give a u dot square. So that is velocity term, and rho into dv, rho is a density, into a volume will give a mass. So which is basically a small mass, that is delta V. And when we integrate over a whole volume, I will be getting what is the kinetic energy of the whole structure. So in the sense, this equation gives a kinetic energy of a given beam. So here rho refers to the density, that is mass per unit volume of the material. And here if I consider in a space in a 3D model, if I take this as mass, then there will be a three component of a velocities. One, velocity in x direction. What is the velocity of this body in x direction? What is the velocity of this in a y direction? And what is the velocity of this body in a z direction? So this is for a three-dimensional the body with a 3 degrees of freedom. So this refers to the u dot refers to the velocity vector of a point at a x with a component u dot, v dot and w dot, which are nothing but the velocities in a x, y, z components. Using a displacement and a safe function relation, it can be written as, we know that this from our first module, wherein u is equal to displacement, u is equal to n into q, where n refers to the safe functions and q refers to the displacement. Now the same thing can be written in a kinematic form as u dot, which is a velocity, is equal to n into safe function into q dot, that is velocity of that. When I differentiate the displacement with respect to time, I will be getting a q dot. So I can write u dot is equal to n into q dot. Now this u dot will be replaced with a n into q dot. So here in this equation, I will replace this u dot with this n into q dot, and it can be written as kinetic energy Te. Te refers to the kinetic energy of an element E is equal to half into q dot T into integral over a volume rho n into n transpose into n into dv. So wherever u dot is there, you substitute with the n of t, you will get this equation. Now this can be written as, this is a velocity term, that is q dot t into q is nothing but a q dot square, and this refers to the mass matrix. So in the sense, I can write me, mass of an element, is equal to integral over a volume, and this term can be written here as a mass term. And here you note that we are representing q transpose, because in order to multiply a matrix, I should have a order matching. So in order to satisfy those conditions, multiplication of a matrix, we take it as a q transpose. So with this, we will derive what is a mass matrix. So let us consider for 1D element, like this was our 1D element, wherein I'll take here the length of the element is say 2, because it is in a local coordinate system. Here it is positive 1 and here it is negative 1. And the safe functions for that one will be like at n1 it will be maximum, and it moves and becomes a 0 at a other node. And similarly, if I take a safe function at n2, node 2, the effect of the safe function is maximum at node 2, and as it moves towards 1, it is 0. So these already we know how the safe functions varies over a element length. So now if I take qt as a q1 and q2, that is a displacement at node 1 and displacement at node 2, then n can be written, n is a safe function, can be written as n1 and n2, which are given by n1 is equal to 1 minus zeta by 2, n2 is equal to 1 plus zeta by 2. Suppose if I say this is 0 and this is n1 and this is n2, and if I substitute zeta here is a minus 1, if I substitute zeta is equal to minus 1, it will be minus of minus 1 divided by 2, so that is equal to 1. So in the sense, the effect is maximum here, our safe function is maximum here, the value of this is 1. Similarly, at node 2, substitute zeta with a 1, it will be again 1. So in the sense the effect is maximum here, and over a node, other node, it becomes 0. Now ME is equal to rho into integral V n transpose into n into area into dx. A into dx will give the dV volume. So that can be written as rho into A into rho. This L by 2 is from this equation. If I transfer the structure from global coordinate to a local coordinate system, then dx will be a L by 2 into zeta. So this dx is substituted by L by 2 into d zeta. And n transpose can be written as 1 minus zeta by 2, 1 plus zeta by 2, which is a 2 row and 1 column. And n is equal to transpose of this one will be 1 minus zeta by 2, 1 plus zeta by 2. There is one row and one column. Now I can multiply these easily because this is 2 into 1 order and this is 1 into 2 order. So I'm satisfying the matrix multiplication condition. So I will be getting a 2 by 2 matrix after I multiply. So now you are clear with why we have taken a n transpose. Now substituting n1 and n2, we get rho 0 to L over length n transpose n A into dV A into dx is equal to rho A L by 2. This is in a global, this is in a local coordinate system. Integral -1 to +1 n transpose n into d zeta. Now substitute wherever n say functions are there, substitute with the corresponding matrices like this. So after we substitute here, you can multiply the row and a column. So this term into this term will give a 1 minus zeta whole square, 2 into 2, 4. Similarly, this term into this term will give 1 minus zeta, 1 plus zeta, 1 minus zeta square, it will be divided by 2 into 2, 4. Similarly, multiply this 1 plus zeta by 2 into 1 minus zeta by 2. So we will get this term. Similarly, you multiply this and it will be 1 plus zeta whole square divided by 4. So once we multiply, you can expand this quadratic terms. So it is of a minus b whole square. So 1 into 1, 1 square plus zeta square minus 2 zeta divided by 4. 1 minus zeta square by 4 as it is, and this term as it is, and 1 plus zeta whole square is equal to 1 plus zeta square plus 2 zeta by 4. Now once we get this equation, we have to integrate each of the elements of the matrix with respect to zeta. So I have to integrate each of them. So I have to integrate this, this, this and this. And for demonstration, I have shown the calculation of this part, and you can do in a similar way on your own. So I have taken here integral of -1 to +1, 1 plus zeta square minus 2 zeta by 4. I have taken this and into d zeta is equal to, that can be integration of, I am taking this 1 by 4 outside. So 1 by 4 into the integration of 1 is zeta plus zeta square is zeta cube by 3 minus 2 zeta is zeta, integration of zeta is zeta square by 2, and the limits are -1 to +1. So now you put the limits here. So put a plus 1, 1 by 4 into, so wherever zeta is there, substitute with the 1. So zeta is 1 here, plus zeta cube, 1 cube is 1 divided by 3, minus 2 as it is, zeta square is 1 by 2, minus, I have to substitute the minus 1 limit, 1 by 4 as it is, into zeta is minus 1. So zeta cube is minus 1 into minus 1 into minus 1, it will be minus 1. So it is minus 1 by 3, minus as it is 2 zeta square, minus 1 into minus 1 is plus 1, so 1 by 2. So upon simplification I will get 2 by 3. In the sense, the integration of this term can be reduced to 2 by 3. Similarly, you can integrate the terms and substitute the limits to all these terms and get the value. So here I have done it as shown. So this term is replaced by this I will keep as it is, rho a into L by 2, this term. So integration of all these terms will be written as, so this term is 2 by 3, that is already calculated here, and integration of 1 minus zeta square is 1 by 3. You can work on this, and similarly these two terms are same, so it will be 1 by 3, and also the integration of this is 2 by 3. Now you take 1 by 3 outside and multiply with this 2, it will become a 1 by 2 into 1 by 3 is 6. So rho a L by 6 into, and retain this 2, 1, 1, 2 inside the matrix, and this matrix is called as consistent mass matrix. So this matrix will help us to solve the dynamic problem in the future sessions. So I will be using this mass matrix to solve the problems, dynamic problems, to find the frequency and displacement of a structure in a later stage. So thank you.